You know that feeling when your thoughts are racing ahead, but your fingers on a keyboard or even your own voice just can't keep up? Well, it turns out that's not just a feeling, it's a hardwired physical limit. There's a fundamental speed limit on all human communication, and in this explainer, we're going to dive into the incredible technology being built to absolutely shatter it.
So let's put a number on that speed limit. It's 39 bits per second. That's it. That's the cap. Research shows this is pretty much the universal maximum speed for human language, no matter what language you speak. When you think about it, that's a shockingly slow pipeline for the supercomputers we all have in our heads.
And this gets us to a core problem, a concept called the biological bottleneck. Our brains are just incredible, right? We've got 86 billion neurons firing in parallel, processing the world in this massively complex way. But to get any of that thought out into the world, we have to serialize it, line it up, and squeeze it through the incredibly slow, narrow channels of our body, our vocal cords, our hands. We're essentially trapping these high-speed thoughts in low-speed bodies.
And this chart, wow, this really puts the problem into perspective. Look at this. The first brain-computer interfaces, or BCIs, they were actually slower than just typing. Our biological best, speaking, tops out at that 39 bits per second we just talked about. But now look at that bottom row. The next generation of this tech isn't aiming for just a little bump. We're talking about a leap to over 1,000 bits per second. That's not just an improvement, it's a whole new paradigm. Okay, so the billion-dollar question is pretty obvious, right? How do we actually do that? How do we make that kind of jump and bypass the biological hardware we've been stuck with for thousands of years? Well, the answer lies in chasing this incredibly ambitious goal, what you could call the dream of instant thought, or as the researchers working on it call it, achieving zero-latency intuition. The idea here is to create what's called a frictionless cognitive loop. This is where the technology gets so fast, so responsive, that it just stops feeling like a tool you're consciously using. Instead, it becomes this invisible, high-speed extension of your own mind, completely erasing the delay between your intention and the action itself.
So what's the actual tech that makes this dream possible? Well, it all comes down to syncing up our squishy biological neurons with cold, hard digital circuits, synchronizing silicon and synapse.
It really boils down to 3 core steps. First up, acquisition. You've got these ultra-thin, super flexible electrode arrays that are listening in on the firing patterns of thousands of individual neurons at the same time. Step 2 is quantitation, and this is super cool. You can't just wirelessly beam all that raw brain data out. It would generate so much heat it would literally be dangerous for the brain tissue. So the trick is to process the signals right there on the chip itself, to simplify them before they go anywhere else. And finally, step 3, processing. That clean signal is then analyzed by local GPUs, completely skipping the internet and all of its lag and unpredictable delays.
And all of this comes together in this really smart hybrid system. Now, don't worry about reading every detail on these diagrams. The key thing to get is that the edge, that little local chip, handles all the split-second, real-time stuff. Meanwhile, the cloud is used for the heavy lifting in the background, for long-term learning and updating the system. You get the best of both worlds. You have lightning-fast reflexes and deep, evolving intelligence. And this right here is exactly why that local, edge-native approach is such a game-changer. The old way of doing things, sending data to the cloud for processing, introduces what's called jitter. That's just unpredictable lag from a busy network. And that's the enemy of a seamless experience. The solution is to do all the time-sensitive work right there, locally at the source. That's how you get a truly instant response. So how do you keep this incredibly high-speed connection stable? Well, engineers are using some seriously advanced algorithms. You can think of them as predictive software that's constantly anticipating and canceling out any potential lag before you'd ever notice it. It even uses AI to learn and adapt over time, making the whole connection stronger. It's this incredibly sophisticated digital balancing act, all happening in milliseconds, just to keep your brain and the computer perfectly in sync.
But look, this technology is so much more than just a cool engineering puzzle. It has absolutely profound implications for people's lives. So let's shift gears and talk about the human impact, from restoring senses that were lost to truly augmenting our reality.
So why does all this low-latency, high-speed stuff matter so much? Well, just look at what people who use prosthetics say they want most. It's not just about better movement. An overwhelming 87% want improved tactile sensation, the ability to feel, and 76% want better proprioceptive feedback. That's that natural, intuitive sense of where your limb is in space without having to look at it.
Let that number sink in for a second. 87%. People don't just want a tool to move things, they want to feel with it. This is about restoring a fundamental part of the human experience that has been taken away.
And that is where these bidirectional interfaces come into play. They create a two-way street for information. So it's not just about sending motor commands out from the brain. It's about sending rich sensory information back in. This is what could allow a user to feel the rough texture of a piece of wood, the warmth of holding someone's hand, or the delicate pressure needed to pick up an egg.
So you can really see how this is all evolving along a clear path. It all starts with getting better and better at acquiring the signals from the brain. Then you shrink the latency by doing that quantization right on the chip. After that, you get rid of cloud delays with edge processing. And the final phase, the end game, is closing the loop with sensory feedback to achieve something called perceptual transparency, the point where the technology just disappears and feels like a natural part of you.
Of course, as we race towards this future, wielding this kind of power forces us to confront some of the deepest, most profound ethical questions our species has ever faced. We are, quite literally, writing new rules for the mind. And look, these aren't some far-off sci-fi problems. They're becoming very real, very fast. Think about privacy. If your brain signals can be read, who owns your thoughts? What about autonomy? If the system is predicting and assisting your actions, are you still fully in control? Then there's identity. How does merging your mind with a machine change your fundamental sense of who you are? And maybe most importantly, equity. What happens to society when this kind of powerful upgrade is only available to the wealthy?
All of this brings us to one final mind-bending question. As we shatter the speed limits of our own biology and our very thoughts begin to move at the speed of silicon, where do you end and where does the machine begin?